So LeetCode 865, smallest subtree with all of the deepest nodes. So for this problem, you just need to return the root of the smallest subtree that contains all of the deepest nodes in the original tree. Okay, so let's look at this example right here. So let's say that you were doing this by hand instead of doing an algorithm for a computer. Let's say that you were doing it by hand. So you are starting at the root because that's the only input that you have. So you start from here. And you want to know where is the smallest subtree that has all of the deepest nodes. So you look to your right and you see that the maximum depth of your right subtree is 2. 0, 1, 2, right? Okay, so this is the maximum depth of my right subtree. Then you look to your left subtree and you see that the maximum depth there is 1, 2, 3. So you see that there is at least one node in your left subtree that has a higher depth than the whole maximum depth in your right subtree. So what that tells you is that you can basically discard all of your right subtree because it doesn't do anything for you because you have at least one node that has a higher depth in your other subtree. So why would you ever go down this path? It's definitely not going to be useful because you want the subtree that has all and only basically, like you want the minimum subtree, so you want to move the furthest down possible that has all of the deepest nodes, and here you don't have any of the deepest nodes, so you just discard this. And now since you've discarded this, you can basically also discard the root node, because I mean, what's the point of keeping it if you're only interested in the left subtree, right? And so what that means is that you can basically travel downwards to your left subtree. And so now you're here and you're left with basically the same problem. Now you're asked to find the smallest subtree rooted somewhere in these trees, and that has all of the deepest nodes. And so yeah, you can just apply the same thing, right? It's kind of like a recursive algorithm. So you can just apply the same thing back again. So you check your left subtree and you see that its maximum depth is 1. And then you go to your right subtree and you see that its maximum depth is 2. And so because of that, you know that in your right subtree, you have at least one node that has a higher depth than all of the nodes in the left subtree. And so that tells you that you can discard your left subtree because there is not going to be any node with the maximum depth there. So you just discard it. And now that you've discarded it, then you don't need your current root node either, because what's its point? Like, it doesn't serve any purpose. So now you just go to this node here, right? So you travel downwards to your right subtree. And now here's the interesting part. Now you see that the maximum depth in your right subtree is equal to the maximum depth of your left subtree. So if you move down any of these two paths, for example, if you go to the right subtree, then now you're missing this node, which has the same depth, right? So you're missing one node that had the same depth. And so you're not satisfying the return condition anymore because you want all of the nodes with the maximum depth. And if you move to the left, then now you're missing this one, right? So what that tells you is that you cannot move any more downwards. You need to stay here. If you move any more downwards, you're going to be missing one of the deepest nodes. So yeah, you just stay here and you return your current root. Okay, so let's implement that. So we're going to have a while loop that keeps iterating while the maximum depth of the left subtree is different from the maximum depth of our right subtree, like this, right? And as long as we check this condition and it is true, then we keep iterating. But if it is false, then we just return the current node, right? And what do we do in the iterations of the while loop? Well, if the maximum depth of the left subtree is greater than the maximum depth of the right subtree, then we want to move to the left. But if this one is greater than the maximum depth of the left subtree, then we want to move to the right, right? So yeah, if the right is greater, move to the right. Else, the only other case that we need to check is, since we know that they are different, is where the left subtree is greater than the right subtree. And so otherwise, so if this is not the case, then it's definitely the other way around. And so you just move to the left instead of moving to the right, right? Okay, and now you just, like, all that's left is to just implement the max depth function, which is a very common recursive function. So you just start with a node and you have your base case, which is if you have no node, so like node is null, so maybe you went down a leaf, right? Then if you have no node, you just return a 0 because your depth is 0. And what if your node actually has some value? Well, in that case, let's say that we are like here as a node with value 5. How do we know our maximum depth? Well, you look at your left subtree and you look at your right subtree and you use the same function again. So you call max depth on those, and whichever has the greatest depth, you add 1 to it because you are an ancestor, right? So you have depth 1 plus the maximum between your two subtrees' maximum depths. Okay, so you just return 1 plus the maximum between the depth of your left subtree and the depth of your right subtree, like that. Okay, now basically this would already work, like it's already a solution, but the time complexity is pretty bad because you're calling max depth on nodes that you've already called it once. So instead, what you want to do is you want to cache the results. You want to memorize them so that you can then return them without doing the computations again. So you just keep a cache, and what you do is you check if you already have a cache value, then you can just return that, right? So you look up your cache, the current node's value. And the reason for which you can use the node's value as a key is because down there it says that the values of the nodes are unique. Okay, so use the node's value as a key in the cache. And if it is not undefined, then it means that you already memorized the value there. Otherwise, you actually need to do the computation. And don't forget to also update the cache when you do the computation. So instead of just returning, we also assign the computed value to the cache in the correct key. Okay, and yeah, that's it. I'm going to submit the solution to show that it works. And the time complexity is O of n, because you go through all of the nodes like once or twice at most if you move through them in the while loop also. And the space complexity is O of n, because you need to keep a cache with all of the values, and also because of the visit, which is recursive, and so could also take up to O of n memory. Okay, so also one more thing, even if the values were not unique, like here it says that the values of the nodes in the tree are unique, but even if they weren't, you could just do the same solution just by using, instead of the value of the node, you'd have to, before doing all of this, go through all of the nodes in the tree and assign a unique ID to them in any way, any arbitrary way. And then after doing that, you can just use the node ID instead of the value, and that's going to be unique, right? So yeah, that's it for me today. Thank you for watching, and bye.